Hi, welcome to Naukri Learning. My name is Kanika Garg and I'm an artificial intelligence enthusiast. I have an experience in machine learning, deep learning, data science, along with Python. Today, we are going to discuss CNN, that is convolutional neural networks and its fundamentals. So these are the topics I am going to touch down in this presentation. First, we will discuss artificial neural networks. Then we'll move on to deep learning. And finally, we'll talk about in detail about CNN. So let's a little talk about neural networks. So neural networks are one of the most significant discoveries in the history that we all agree. And they in 1970. It's a subset of machine learning and they, of course, works at the heart of the deep learning. So neural networks basically reflect the behavior of human brain, allowing computer programs to recognize patterns and solve common problems in the fields of AI, machine learning, deep learning. Whatever comes to our mind these days, neural networks have the answer. So we say that that neural networks are the core to understand CNN. As you can see here in the diagram in the figure, it has various layers. For very first one is the input layer, then it has some hidden layers, and finally the output layer. So here each node is connected to other nodes and has the links has some weight and biases along with them, which tells which neurons or which nodes will fire. If the output of any individual node is above the specific threshold value, the node is activated, sending data to the next layer of the network. Otherwise, we say the no data will be passed from one layer to the another layer if the neuron will not, if the neuron is not firing. So this is the basic structure, and we are going to go in detail for CNN. Now, let's talk about deep learning. We have probably seen terms like artificial intelligence, machine learning, and deep learning flying all over the place in our social media news feeds, right? And somehow we use them interchangeably. But then we must understand that the parent of the deep learning is basically the artificial intelligence, and a small subset of artificial intelligence is machine learning. And similarly, the deep learning is a subset of the machine learning. So before going into the deepers, we must understand about deep learning. And the deep learning revolution started in some 2010. And since then, deep learning has solved many unsolvable problems, or it has solved many problems that took eventually a longer period of time in a very short durations. So deep learning revolution was not started by a single discovery. It more or less happened when several needed factors were ready. Like we have high computational complexities and higher computer storages, better training methods and better algorithms, better tuning methods. So these all contribute for the development of these deep learning methods. So as in the graph also, we can see somehow the older algorithms tend to achieve a stagnant performance very soon, whereas deep learning keep on learning when we feed data to it. So at its simplest, we say that deep learning can be thought of as a way to automate predictive analytics. And while traditional machine learning algorithms are like, they are linear, and deep learning algorithms are, say, stacked in a hierarchy of increasing complexities and abstractions. So let's take an example to understand deep learning in a better way. Imagine a toddler whose first word is dog. The toddler learns what a dog is or what a dog is not. I mean, he can recognize by seeing an animal whether he is a dog or not, by pointing to the objects and saying the word dog, right? So the parent says, yes, that is a dog, or no, that is not a dog. So as a toddler continues to point to objects, he becomes more and more aware of the features that all the dogs generally possess, the common features. So what the toddler does, without knowing it, is clarify a complex abstraction, the concept of the dog, by building a hierarchy in which each level of abstraction is created with knowledge, and that was gained from the preceding layer of the hierarchy. That means initially he has just learned the common features that it has a tail, it has four legs and two eyes. Then eventually he has learned, okay, it has a nose like that, it has a mouth like that, and the tongue like that. So the initial learning was like what the basic features, and then the more it goes deeper, the more detailed features the toddler has learned. In the very similar manner, deep learning works. So the word deep comes from many layers. That means it has many layers. That means it goes very deep. Generally, the deep learning models has various layers from where the input travels and uncovering the various features from the data, whereas each hidden layer will perform the kind of feature extraction method for different features. This is exactly how a deep learning network looks like. We are feeding them an image and it will goes to various hidden layers. And then in the final output layer, we will get the category of the image, whether it's a dog, bird, or a cat. Now, moving on to CNN. Let's talk about the very basic concepts first. Convolutional neural networks, also called as CNNs or ConNets in a common language, and they are type of a feed-forward artificial neural networks whose connectivity structure is inspired by the organization of the animal visual cortex. Now, convolutional neural network is generally used to analyze visual images by processing data with grid-like topology. It is also known as ConNet. The convolutional neural network is generally used to detect and classify various features or objects from an image. So when we want to extract, say, features from the image, we have to analyze the image, and image is nothing but a matrix of different pixel values. So every image is a combination, or say the matrix of the different pixel values as depicted in the diagram. So imagine our image is a digital, standard digital camera with 3 channels generally. So whenever we want to describe any image, and we have 3 channels, and we can have YMK, we can have RGB, or we can have the grayscales if the picture is black and white. So here in the image, we can see that it is a RGB image and it has 3 channels. So each of the channel has its own unique image values for the pixels to depict the image in a proper manner. So imagine those 3 2D matrices stacked over each other for red, green, and blue, one for each color, and each having pixel values that ranges from 0 to 255, right? For grayscale image, we have one 2D matrix because it has only one channel, and each pixel value will again range from 0 to 255. Where 0 will indicate black and complete 255 will indicate white color. This is how CNN recognizes images. If you see in the very first image, it is making a symbol of the backslash, and if on the right side, if you see, the image is making a symbol of the forward slash, right? So now if you can see in this image here, this is depicted in the pixel format here in the second image. When it is transformed to the pixel values, we see the values of 1 wherever the black was prominent. So from here, we can see how an image can be represented in the form of black and white pixels, and finally in the form of the matrix with the integer values. So this is how any CNN will recognize an image. Okay. So convolutional neural networks have an input layer. They have then the output layer and the numerous hidden layers and the millions of parameters, which allow them to learn complicated objects and patterns. As you can see in the figure, for feature learning, or say for the hidden layer, we have various other layers called as the convolutional layer, then the pooling layer, and various combinations of them. Then we finally flatten them and then we have a fully connected layer, the softmax function, and finally the output. We will go on further and discuss them in details. So let's moving on to the next slide, and let's see the complete working of the CNN and understand it. For the input image, we fed it the matrix of the pixels to the convolutional layer. Then convolutional layer will act upon it and send it to the pooling layer. Then pooling layer will fetch the important features and will reduce the dimensionality. And finally, it will flatten the matrix and send the flattened output to the final layer to the fully connected layer. Now, I have been saying this convolution layer, convolution again and again. What exactly convolution is? Now, convolution layer is the core building block of the CNN. It carries the main portion of the network's computational load. Now, this is the first step in the process of extracting valuable features from an image. A convolution layer has several filters that perform convolution operation. Every image is considered as a matrix of pixel values. Like here we have, now if you can see, there is some multiplication going on with the yellow boxes. So if you see, it has the value of 1, 0, 1, 0, 1, 0, and 1, 0, 1. So this matrix is being multiplied by the parts of the actual image, and we are getting this convolve feature. What exactly it is doing is we are filtering some features from the actual image, and this is where we are multiplying it, is called as the filter matrix, which we will use to extract some kind of features. And what the features could be, we can see further. So basically, what exactly this layer is doing, this layer is performing a dot product between two matrices, where one matrix is the set of learnable parameters, otherwise known as kernel, and the other matrix is the restricted portion of the receptive field. This means that if the image is composed of 3 channels, the kernel height and width will be small, and the depth extends up to all 3 channels. Now, if you see here, we have here values for 3 channels, red, green, and blue, and the pixel values. We have 3 filter values, or say kernel channels. If you see that by multiplying this kernel with this set of operations or all the values, we are getting some values, and with these values, by summing up, we are creating a final output of this layer, which is called as the convolved feature. What exactly we are doing? We are learning some features in this layer. So here, what exactly is happening? The filter moves, this filter or the kernel moves to the right with a certain value, which is called as stride, that we will learn in further slides, till it passes the complete width. Moving on, it hops down to the beginning left of the image with the same stride value and repeats the process until the entire image is traversed. In case of images with multiple channels, as we are seeing here with RGB, the kernel has the same depth as of the input image. That means the depth would be like here, we have 3 channels, so kernel also will have the depth of 3. So the objective of basically the convolution operation is to extract the high-level features such as edges from the input image, and these not to be limited to one convolution layer. We can have multiple convolutional layers depending upon the features we want to extract. Suppose in the very first layer, we just have extracted the outer shape and the edges. Then in the next, we can extract the more detailed features like eyes, nose, and all. So with added layers, the architecture adapts to the high-level features as well, giving us a network which has the wholesome understanding of images in the dataset, similar to how we would understand. Now, I've talked about kernel, or say filter. So every filter has certain capability to extract a feature. Now here, if a kernel is 3 cross 3, so it will shift like 9 times because we have a stride length of 1. So what stride is, we'll discuss. So now convolutional layers are composed of weighted matrices called filters. So filters slide across the image from left to right. If we can see here in the image, it slides right from here to here in the manner of this, right? It will start from the left, moving on to the right, and finally taking input only a sub area from the image. So we will see how this local connectivity between the activated nodes and the weights will optimize neural networks performance. So filters, will activate when the element-wise multiplication results in positive values. This informs the network of the presence of something in the image, such as a feature that we want to see, like the edge or the eyes, or maybe the darkness or the lightness, depending upon the image, or maybe a particular blotch of color. Now, kernel has, okay, before going on to the details, let's see here. If you see here in the very first layer, the very first hidden layer, it is recognizing only the edges. Then in the second hidden layer, it is recognizing the corners and the contours of the image. In the third hidden layer, the object parts. Okay. And then in the final output layer, it will recognize whether it's a car, person, or an animal. This is how a CNN will work with multiple layers. So each hidden layer will have its own convolutional layer. Similarly, for the second hidden layer also, it will have its own convolutional layer, which will be responsible to identify corners and contours. So filter has its own parameters called as hyperparameters. So it has 2 parameters that will impact the size of the output volume of each filter, that is the stride and padding. Now, if you have noticed that we were moving filters across the input matrix one by one. So it happens when the stride value is 1. So it is basically the distance that filters moves at a time. So generally speaking, the smaller the steps you take when sliding the filter over an image, the more details will be reflected in the resulting feature. It also means that more features will be shared between the outputs, since large portions of the filters will overlap, right? So if we increase the step size, that means if we increase the stride value maybe to 2 or 3, fewer parameters are shared between filters and feature map will be smaller. So applying a larger stride basically has the effect of downsampling the image so that lower level details can be avoided. So when the stride is 1, then we move the filters to 1 pixel at a time. And when the stride is 2, we move the filters to the 2 pixels at a time, and so on. So basically stride helps to reduce the size of the image, particularly a useful feature. This dramatically reduces the model's computational complexity, and it will definitely help us to, save our some time and effort. Now, let's see, why do we need padding? When we perform a standard convolution operation, the image shrinks by a factor equivalent to the filter size plus 1. So if we take an image of the width and height of 6 and a filter of width and height of say 3, the image shrinks by the following factors. Say, suppose if 6 is the dimension, like 3 is our filter, and 1 is the plus 1 is we add in the formula. So what exactly we have is 4. So the convol feature that we get after stride is, or say after convolution, we have 4. So the reason for the shrinking image is that 3x3 filter, if we are using 3x3 filter, cannot slide all 3 of its columns over the first 2 horizontal pixels in the image. The same problem exists with regard to the rows and the vertical pixels. So there are only 4 steps left for the filter until it reaches the end of the image, both vertically and horizontally. As a consequence, the resulting image will only have 4x4 dimensions instead of 6. So this entails two problems. One is if you perform multiple convolution operations consecutively, the final image might become vanishingly small and the image will shrink with every operation. And the second one would be because you cannot slide the full filter over the edge pixels, you cannot perform full convolutions. As a result, we will lose some information around the edges. So to address this problem, we apply padding. So to apply padding, we have two standard procedures that is called as the same padding and the valid padding, as you can see in the diagrams itself. When padding is same, it means it's a process of adding enough pixels at the edges so that the resulting feature map has the same dimensions as the input image to the convolution operation. And if for the valid padding means that we only apply a convolution filter to valid pixels of the input. Since only the pixels of the original image are valid, valid padding is equivalent at no padding at all. So now depending upon whether we really want the pixels at the edges to be recognized properly and how much accuracy we want, how much more emphasis we need to have on edges, that will now depend on how we choose our padding. So then moving on to the activation layer. Now, this is exactly a part of the convolution layer if we try to understand, because after convolution, we have an activation layer and then we come on to the pooling layer. Now, at the end of the convolution layer, the input image has been transformed into a stack of feature maps. Now, each feature map corresponds to a visual feature seen at specific locations in the input image. For example, the edges, the contourings, and all. These feature stack size is equal to the number of nodes in the convolution layer. Now, activation function determines the relevancy of a given node in the neural network. A node relevant to the model's prediction will fire after passing through an activation function. And if that node is not relevant or the feature is not relevant, it will not fire. So for activation, in this, we use ReLU, which is basically rectified linear unit. Once the feature maps are extracted, the next step is to move them to the activation layer. And here it is called as the ReLU. ReLU performs element-wise operations and sets all the negative pixels to 0. So we say the negative pixels 0 means that they will not fire, and it introduces the non-linearity to the network and generates output generates the output only if the value is 1. That means if the value is 1, if it has a positive pixel, then only the node will fire. So the main advantage of using this ReLU function over other activation function is that it does not activate all the neurons at once. For the negative input values, the result is 0. That means the neuron does not get activated. Since only a certain number of neurons are activated at a time, the ReLU function is far more computationally efficient when compared to sigmoid or other activation functions we have. So this is how activation layer will work. First, we will have an input image from, in the form of RGB. Then it will go to the convolution layer and will create a feature map. Then it will go to the activation function and we will have a rectified feature map. So if you can see here, all the negative values have been made 0. That means they will not fire. The nodes associated with these values will not fire. Only the positive values will fire. Then the very next step we have after activation is the pooling layer. And we see that we know in the convolution layer, we have a stack of visual feature maps, right? As the complexity of a data set increases, so much the number of filters in the convolution layer. Each filter is being tasked with the job of identifying different visual features in the image. So as we increase the number of feature maps in this stack, we increase the dimensionality, parameters, and the possibility of overfitting. So pooling layers are generally comes handy for this purpose because we want to reduce the size of the inputs and hence speed up the computation. Or we also say that it helps in reducing the dimensions. So for pooling, we have two types of pooling available for us, like the max pooling and the average pooling. As you can see in the diagram itself, in the max pooling, if you see here, in the max pooling, we consider each block and we find out the maximum value it has to put it here. Similarly, then the next one, it has a maximum value of 30, it will come here. Here it has a maximum value of 112 and here 37. So in the max pooling, it is basically used most for image classification. This decision runs off the assumption that visual features of interest will tend to have higher pixel values, and max pooling can detect these features while maintaining spatial arrangements. So this is how, and this is why max pooling is relevant for image classification. Now, if I talk about, say, average pooling, if you look closely here, the values that are assigned here are the average of all the values in each quadrant. Now, if you say 12, 28 and 12, 28 and again 12 divided by 4, it will give the average value of 13. So in average pooling, we calculate the average of all the values and assign that value to the image. So with global averaging, the feature maps dimensions are reduced drastically by transforming a, say, 3D feature stack into one-dimensional vector. The values of all the pixels are averaged and outputted to a single node in one-dimensional vector. This results in a k dimensions where k is the total number of feature maps. So this is how our pooling layer works. After doing all that work, we have a simple work left for fully connected layer, which finally helps in achieving our goal, which is exactly the making the class predictions, right? So after our input moves to the convolution layer, from convolution layer to function, activation function, then pooling layer, it finally arrives at the fully connected layer. Now recall that fully connected neural networks are constructed out of layer of nodes, wherein each node is connected to all other nodes in the previous layer. This type of network is placed at the end of our CNN architecture to make a prediction given our convolved or learned features. So the goal of fully connected layer is to make class predictions. The layer will take input, a flattened vector as an input. So whatever we create after pooling layer, we create a vector, flattened vector. That means a single array or a vector that have been activated in the previous convolution layers. This vector input will pass through 2 or 3, maybe some dense layers in the fully connected layer, and finally to the final activation function before being sent to the output layer. So the activation function used for prediction does not need to be ReLU. So it could be softmax, sigmoid, that depends on our priorities. So for so we have different options to use for the activation functions here that will depend upon our usage. So we can favor sigmoid. Sigmoid is generally used for binary classification problems such as say logistic regression functions. And softmax, we generally ensure that the sum of the values in the output layer sum to 1, and it can be used for both, say, binary and multi-class classification problems. So finally, the output vector size should be equal to the number of classes we are predicting. So finally, the output layer will have that number of nodes in which we want to predict the output to. So suppose if I have, say, for sentiment classification, I have 2 classes, positive and negative, then this output layer will have 2 nodes. So the fully connected layer is learning a possibly non-linear function in that space. So this is how the complete CNN works. And now coming on to its various applications, where we have, say, spatial data, we can apply CNN like weather data, facial recognition, or documents. CNN has solutions for all of these. So it is really helpful in facial recognition and especially the climate or the weather data, where we have huge amounts of images available to analyze. For such cases, CNN proved to be a boon for us. Now, these are the various courses that you can go through. These are well-curated courses provided by Udemy and other websites. And the links are also provided. If you want to go in details for these courses, you can access these courses. Finally, thank you for bearing with me. If you like the video, please hit like and subscribe to this channel, Naukri Learning. Thank you so much.